Namaste and good morning. We are here today on the occasion of National Space Day, 23rd August. I'll be telling you a little bit about India's space program, its past, its present and its future. My name is Bhas Bapat and I am a professor of physics at the Indian Institute of Science, Education and Research, Pune. I have been fortunate to be part of this space journey for a short time and it has fascinated me. I hope it will fascinate you too. Let us delve a little bit into the history of our space program today. It might seem like a very unusual thing for a space program to start, but our space program actually started in very humble beginnings, in very humble surroundings, in a church at the southernmost tip of the country, Lady Magdalene Church in a fishing hamlet called Thumba in Kerala. The year was sometime in the 60s. This church was a church for the fishermen of that hamlet. But this church also happened to be on the magnetic equator. For this reason, that site was thought by the pioneers of our space program to be appropriate for the launching of rockets. The fisher folk agreed to hand over this church for a national mission. That's where this history begins. This church today is a space science museum, part of the large Vikram Sarabhai Space Center at Thumba in Kerala. Like many things, Indian space program started small. Vikram Sarabhai, the then director of Physical Research Laboratory, Ahmedabad, put together a bunch of motley crowd in the early 60s. He thought that the nation needs to get into the space program for its own development, and we had to develop the program ourselves and not just depend on the industrially advanced nations to do it for us. In 1962, as part of the then Department of Atomic Energy, a national program for space research called INCOSPAR was initiated. INCOSPAR later morphed into what we are now familiar with, that is the Indian Space Research Organization. Vikram Sarabhai was a visionary. He was also a great leader. He was also a great communicator and he could relate to people very well. I have been fortunate to be part of the Physical Research Laboratory for a fairly long part of my career, and I have heard many very amazing stories, very encouraging and motivating stories about Vikram Sarabhai. The need for the space program was very strongly emphasized by him and many others with him, and the government was convinced that this was something worth pursuing and it would lead to nation building and development. So, in 1972, a separate Department of Space was formed, and the Department of Atomic Energy and Department of Space became two large science and technology departments of our country. What were the objectives of this program? Now, if you reflect back on the 60s was a time when the nation was facing several challenges, and at this point, putting our resources into what seemed like a very esoteric objective and a technologically challenging and a technological challenge didn't seem like a very great idea to a lot of people. So, what was the thinking behind the space program? There were three major objectives, and all objectives were related to nation development. The first of the objectives was to improve communications to provide a backbone for robust communication services within the country. The second was to carry out surveillance and thereby aid in disaster management, and also of course surveillance and remote sensing for mapping our very large and very varied country. With so many variations, with so many such diversity and such difficulty in communications at that point, it was necessary that all three factors be taken into account to ensure development of the country. Now, the technological challenges of those times were immense. We had barely moved into the industrial era. We were barely getting some industries, self-sufficiency in some industries. And at this point, developing a very high-tech satellite program was really, really hard. But the founders of the space program did not wait for all things to be developed within the country. They started small, they started in multiple ways by taking help from nations which already had some space pedigree, like the Russians, the Americans and the Europeans. And already in the mid 70s, which is about 6 or 7 years after ISRO was founded, we already had TV programs for farmers and teachers, giving them assistance, instructions, warnings, lessons or whatever you like, basically to help them do better farming, better teaching and so on. On today's scale, these programs might seem very small, but remember that in the 1970s, mid 1970s and late 1970s, reaching out to a few 100,000 people by just one simple, not so simple, but by one means of communication was really a great achievement. The communications part of this space program took off in the late 70s with the help of some European satellites, and satellite based telegraphy and telephone systems in a rudimentary form got established in the late 70s. Up until this time, the space program was two-pronged. One was to provide information or programs or assistance to different sections of the society using already existing satellite technology from the West, but using it for our purposes in a very small manner. And the second part of this, or the second aspect of this program, was to develop our own satellites to do the tasks that lay ahead of us. So, progressing on the second front, the Aryabhat satellite was launched in 1975. This satellite was built in India, but was launched using a Soviet rocket, because in 1975 we did not have a rocket that could take us into space. But the work that was being done in the 70s is very fascinating. The work done towards building rockets was very fascinating, although in 1975 for our first satellite we had to rely on a Russian rocket. Here you will see some pictures from that era. On the left is the Nike Apache rocket, which is on a launch pad close to this church that I showed you. This is on the coast of Tumba, and this station is called TERLS, or Tumba Equatorial Rocket Launching Station. This station still exists, although it is not in much use. It is used only for very small rockets. But in the early years, we started small. We had rockets that could only go to a very short height. By short, I mean tens of kilometers. And these were mostly used for studying the atmosphere. If you look up the web or look for some information here and there, you will probably come across what are called, across the term, what are called sounding rockets. Okay, so it is this class of rockets that were initially launched. The resources available were very, very limited. So you can see that some parts of the rocket are being transported on a bicycle. There are some very famous pictures showing how frugal the space program was. People working in very small, very minimally equipped areas or stations or offices, but still pursuing this goal of getting an Indian rocket into space. On the right you see a picture where a helicopter has hoisted a satellite. Now you might wonder what a helicopter is doing to launch a satellite, but this exercise was merely to establish remote communication between the satellite and the ground station. So the helicopter carried this satellite and ground communication was established, confirmed, tested, while this helicopter hovered with the satellite hanging without any wired connections. So this was the beginning of telemetry that is so important for controlling and steering and getting data from any satellite. So it is this kind of very frugal beginnings that our space program has had. A large number of people were involved in this, and all of them very dedicated people, I would say, who initiated the space program, built up a lot of things from scratch. And in this picture you can see some real legends. At the center here in a kurta pajama is Vikram Sarabhai. To the left, the person who is explaining what this equipment is about is Dr. Abdul Kalam, our future president, and also the head of the Defense Research Development Organization, and later also responsible for our missile program. Here in the corner is Madhavan Nair, who later went on to become the head of ISRO and also one of the major architects of our GSLV program. In the other picture is again Dr. Kalam with one of the most important men of the time, Professor Satish Dhawan. Professor Satish Dhawan was actually the one who took our space program from its very early rudimentary beginnings to become a well-established, powerful space program. Many of you might make the connection that our spaceport, our rocket launching station at Sriharikota is named after him. It is called the Satish Dhawan Space Center. So this entire journey of moving from satellites that could be launched by some foreign rockets, for example, the Soviet rocket or one of the European rockets. From that stage we graduated to developing our own rockets, and in 1980 we launched our first satellite and rocket combination successfully from the Sriharikota Center. The date was 18 July 1980. The rocket was called Rohini RS-1, the spacecraft was called Rohini RS-1, and the launch vehicle was called Satellite Launch Vehicle 3, the third version of this, which was the first successful rocket launch from our shores. There were many difficulties on the way, and previous versions of this SLV had failed, but persistence and willingness to correct oneself finally triumphed, and in 1980 we had our first rocket launch. The purpose of this rocket was very modest. It was a small payload, about 40 kilograms, and it contained some sun sensing, very modest sun sensing equipment, and some equipment for making magnetic field measurements in a low Earth orbit. So this was not a payload that went very far, but it orbited around the Earth at a certain altitude. And with this launch, we became the fifth nation with the capability to launch its own satellites. Previously, of course, Russia, followed by the USA, Japan and China were the nations that had launched rockets in space. The Rohini set of satellites then there were multiple versions of this in the coming years, and small increments were gradually happening. But the next major step in the rocket technology was achieved in 1994. Moving from small rockets which could carry payloads of the size of say 40 kg, 50 kg, 100 kg class satellites, we moved on to satellites which could carry much larger satellites. at the beginning a few hundred kilograms, 804 in this instance, which is the PSLV D2 or the Polar Satellite Launch Vehicle, the D2 version of that, which had its first successful flight in 1994. There were a few failures before this also for this PSLV satellite, but finally in 1994 we succeeded. The first satellite that was put out was by this rocket was IRS-P2, and IRS actually stands for Indian Remote Sensing Satellites. This IRS is actually a series of satellites from that point on until as early as very recently, where an entire series of satellites has been designed, fabricated, launched and operated over the period of the last 20-25 years in order to carry out remote sensing work for the country. This satellite was, again relatively modest by today's standards, 800 kg, but you can imagine how big this is compared to the Rohini satellite. Okay, so you can see that this Rohini satellite at the back of a truck, which gives you an idea of its size, and here you will see that the truck is, you can see humans on this in this picture, and you can imagine how much bigger this satellite is, this rocket is compared to the old ones. Now, I'll like to add a word about how satellites and rockets actually operate, just in order to clarify a few things. Okay. Now, whenever we talk of a space mission, it usually has multiple components. The first component, of course, is everything that happens on the ground, but then you need a vehicle to take the satellite, which is actually the instrument that works in space, from ground to its intended orbit. That is done by a rocket, which is like this PSLV D2, and the satellite which sits in the top of this at the top of this rocket in this closed enclosure, that is where the satellite sits, like this satellite IRS-P2, which is there on board the PSLV. Once this is launched in space and a desired orbit is achieved, this satellite is now on its own. The rocket is gone. It has fired, done its job of sending the satellite up, and it has fallen back to ground. While falling back to ground, it usually burns away. But now the satellite is on its own, so it has to carry some fuel, and it also has to communicate with the ground. For this to happen, the satellite also needs to carry some fuel. And when I say satellite, I really mean an object that is going around the Earth. At a later point, we'll make a small distinction between a satellite and a spacecraft. And a spacecraft is something that is more autonomous, goes to a greater distance, and doesn't necessarily stay in orbit around the Earth. But when I say a satellite, when I call something a satellite, it actually does some orbiting around the Earth, and various kinds of orbits are possible. So, one of the orbits which is mentioned on this slide is a sun synchronous polar orbit, which means that the satellite goes around over the poles in some kind of elliptic path, and its orbit is synchronized in such a way that the satellite can always keep pointing towards the sun. Okay. And these kind of satellites are usually in orbits which are favorable for carrying out surveillance or mapping of the terrain. Okay. With the launch of this PSLV and reliable repeated launches, the PSLV actually became the workhorse of ISRO. Over the years, PSLV has launched a very large number of satellites, and with improved versions of the PSLV, larger and larger payloads became possible. Today, PSLV can launch about 2 tons of payload, and it has gone through several launches. I think the current version of the PSLV is some 57th or 58th launch of this same rocket. Now, what are the kinds of satellites that this has launched, and what are the purposes? Remember that the founding members of the space program had this very clear vision that the satellite program should provide service to the country. And the kind of services that these satellites have provided are broadly in the area of mapping, remote sensing, disaster management and communications. Okay. The next big step in the history of ISRO is the development of an even larger rocket, the GSLV. Okay. So, the GSLV program started in 2001. There were some unfortunate failures in the early phases. So, 2001 to 2010 is the development phase of the GSLV, including some failures. Now, these failures didn't again, it was of course a setback for the program, but it didn't necessarily stop progress. Okay. People put in a lot of effort, corrected whatever had gone wrong, and finally the GSLV program also became as robust as the earlier PSLV launch vehicle. And with the GSLV, it became possible to launch even heavier satellites, and in a low Earth orbit, which means that the satellite performs a very large elliptical moves on a very large elliptical path around the sun, around the Earth, at a relatively small altitude, like tens of kilometers or maybe hundreds of kilometers. Okay. And the GSLV could launch a satellite as heavy as 6,000 kilograms, compared to just the 40 kg that the Rohini satellite was. So, in a time of about 30 years, we had progressed from launching very small satellites to very large satellites. The GSLV is also capable of carrying payloads to the geostationary orbit, which is a much higher orbit, 36,000 kilometers. It can carry a payload of 2.5 tons. Okay. This rocket, again, as you can see, in comparison to the PSLV, is a much larger rocket. It also requires a much more elaborate space station, much more complicated technologies, and so on. But this now again has become the second workhorse of ISRO for launching satellites. Apart from developing these rockets and developing satellites for various purposes, over the years ISRO has also offered its rocket launching services to other nations, and every once in a while ISRO puts out satellites for other countries. So, from the point where we depended on other nations to send our rockets, we are now in a situation where we can send other people's rockets, other people's satellites using our rockets. So, if you look back from the time around 2010 or so, we have had a whole series of satellites being launched, being put into operations. Some failed, but a large number of them have succeeded. And over the years, the success rate has constantly gone up. We have a whole set of satellites dedicated to doing what the space program actually started for the objectives that the space program was started, which is communications, a main chunk. There is mapping, there is remote sensing, there is imaging, there is weather forecasting, and so on. Another new aspect that has come in, which probably the founding members did not imagine, was navigation. Okay. So, you now have systems where satellites can guide ships and aircraft, and there are systems in place to do so. The other thing that gradually happened, okay, and this happened much later, is that once the ability of a space program to launch different kinds of satellites for very specific applications matured, there was gradually a thought that perhaps it was now time to undertake missions which had purely scientific merit. Okay. We already had this PSLV series of rockets, which today has about 60 or so launches already, and the GSLV, which has about 10 launches or so. In addition to this, we have also used launch vehicles of other agencies at times when we did not have our own satellites or our satellites, our rockets, or at a time when our rockets were not powerful enough to launch the kind of satellites that were needed. For example, the INSAT series of satellites has often been launched using the French space agency. So has some of the GSAT satellites, GSAT series satellites, been launched using the French spaceport in French Guyana. But barring these, we have now come to a stage where we are capable of launching our own satellites to low Earth orbits, to geostationary orbits, and so on. With this kind of mature program, this kind of stable program going on, the focus gradually changed, and people started thinking in terms of what more could be done other than providing applications. Now, if you have a look at ISRO's website today, you will see this very nice diagram or very nice picture, which shows the number of spacecraft missions, number of satellites launched, number of satellites that we have launched for other people, and the kind of different kinds of programs that are underway. Okay. Now, I would like you to pay attention to some of the things on ISRO's website, which are these data portals. Okay. So, I have listed 3 of them here, MOSDAQ, Bhuvan, and Bhunidhi. These are all portals where data from our own satellites is available in the public domain, and this data is related largely to mapping, weather forecasting, climate, disaster warning, and remote sensing. Okay, so, they are with different purposes for different obtained from different satellites and so on, put together for people to use. The availability of these satellites has improved our weather forecasting capability. It has provided information on impending disasters like cyclones and so on. And more importantly, which is something that we almost now take for granted without even thinking about it, is a very, very strong communications backbone. A large part of our communications backbone, including this talk that you are hearing from IISER Pune, travels to you via a gigantic communication network, and this gigantic communication network is supported by satellites. So, this entire INSAT and other set of satellites, which continue to be launched every once in a while, provide the backbone for all kinds of communication. Let us now look at the third phase of the way ISRO or the Indian Space Program has developed. So far, we have looked at the development of rockets. We have looked at what kinds of satellites have been launched in order to meet the original objectives of the space program. That aspect continues. We continue to launch satellites for those purposes, but over time a gradual shift in emphasis has happened. We have now attempted and succeeded in launching satellites with a very clear focus on exploring space and not just using satellites for specific development related purposes. The first such instance was May 2003, when a small payload called SOXUS and another one called CRABEX, which were 2 small scientific instruments which were flown on board GSAT-2. Then there is Chandrayaan, the entire series 1, 2, 3, 3 satellites, or actually I should call them spacecraft, 3 spacecraft launched at different times in order to explore the moon. Then we had the Mangalyaan spacecraft, which was launched in November 2013. Then the AstroSat satellite, which is an orbiting satellite, which was launched in September 2015 and is still functioning. Chandrayaan-2 in 2019, Chandrayaan-3 in 2023, and more recently Aditya L1. Let us now look at what these satellites were meant for and what have they achieved. Okay. So, the first of these, which was actually a very small attempt, was the Solar X-ray Spectrometer SOXS, and the CRAB-X, which was a radio beacon experiment. These two satellites, or sorry, these two instruments on board GSAT-2 were primarily tasked with two things. The SOX payload was looking at the X-ray emissions from the sun, and the CRAB-X instrument was carrying out ionospheric studies. So, Earth's ionosphere, which would, the ionosphere reflects radio waves, and these radio waves can be reflected either from the Earth back to the Earth, or if you have a satellite at a height above the ionosphere, it would reflect back from the satellite, the ionosphere would reflect it back to the satellite. So, this GSAT-2, which was a geostationary satellite, had these two experiments, and fluctuations in the ionosphere, variations in the ionosphere, how the ionosphere behaves, etc., could be studied by bouncing off radio waves from the ionosphere. The CRAB-X experiment was designed for that. The SOX experiment was looking at the sun, looking at the X-rays emerging from the sun and studying the sun. The next big thing was Chandrayaan-1, but we will come to that in a little later. Another major mission was Mangalyaan, which was in November 2013. This was an ambitious mission because this was the first time that we were planning to go far away from the Earth to Mars, and this was not just a very long journey, it was also a journey fraught with many uncertainties, because as you go further away, you have to struggle with many different kinds of problems. First of all, communication to the spacecraft becomes harder. You need more power, you need better pointing, and you need much better guidance to make sure that the spacecraft does not lose its trajectory and it ends up just getting lost in space instead of reaching its desired target. So, the Mangalyaan was indeed a very ambitious and a very challenging mission, but with a very clear emphasis of exploring the surface of Mars. There was no plan to land on Mars. This was going to be an orbiting mission, but during the orbiting it would observe the Martian atmosphere and the Martian terrain. Okay. The mission was extremely successful. We had very good guidance systems, and the entire program was timed very well regulated, very well studied, very well planned, and we reached, we meaning this satellite, this spacecraft, reached the Martian vicinity according to the planned trajectory, planned timing and so on, and was captured into the Martian orbit in the very first attempt. This is not a feat that any other space program has achieved. Once it was captured into the Martian orbit, Mangalyaan sent back, of course, images, but it also did some studies of the Martian atmosphere. One of the things that it found was the existence of argon and very energetic argon atoms in the exosphere of Mars, and it also showed that the relative abundance of carbon dioxide and oxygen in the Martian atmosphere changes, although it is true that much of it is carbon dioxide, there is also some oxygen there, and the variations in oxygen and carbon dioxide concentrations were studied by the instruments that were on board Mangalyaan. Similarly, it also could map, or it also could observe the variations in what is called the optical depth, which means that if you send a beam of light, how far does it travel before its intensity dies out. That is roughly what atmospheric optical depth means. And this optical depth could be affected by various factors. The fact that this optical depth varies means that there are changes happening in the atmosphere, and this is something that the Mangalyaan mission could demonstrate using its instruments. Yet another major scientific mission was ASTROSAT. Now, ASTROSAT is a satellite, not a spacecraft, because it continues to, it is basically designed to orbit around the Earth, and this has been in operation since September 2015. Okay. This spacecraft or this mission was launched with a very clear scientific objective, which is to carry out multi-wavelength astronomical observations. And when we say astronomical observations, it means everything that can be seen, not just the sun or not just the moon, but everything that can be seen in the sky. The advantage of sending such a satellite and not putting instruments on the Earth is multifold. One of the biggest difficulties or drawbacks in having instruments on the Earth is that not all parts of the electromagnetic spectrum reaches the Earth. Okay. There are several parts in the electromagnetic spectrum that get absorbed by our atmosphere. We only receive some bands or some wavelengths. If you want to study what is emitted in other bands, you clearly have to leave the Earth's atmosphere. So, the ASTROSAT is a low Earth orbit satellite that keeps going around the sun, around the Earth, but it can be made to point in different directions, or it points in different directions at different times, and as a result it can have virtually cover the entire sky, and using its multiple instruments it covers different bands of light or electromagnetic radiation that is coming to us from different corners of the universe. ASTROSAT has been one of the very successful satellites, scientific satellites, and this is still operating, and it continues to put out a lot of scientific information, and many research publications have emerged out of the data that ASTROSAT has sent us. Let us now come to the series of missions to the moon, which I am sure a lot of people know about or have heard about. It was something that actually catapulted the entire nation into believing that we could do something, and left many people on the edge of their seats when this Chandrayaan mission was about to reach the moon. So, in 2008, Chandrayaan 1, the first of this series, was launched, and this was going to be again an orbiter only mission. And remember that although I am talking about Chandrayaan 1 after Mangalyaan, Chandrayaan 1 actually was launched much before Mangalyaan. So, Chandrayaan was the first such mission to go away from the Earth's orbit, or not remain in the Earth's orbit, and actually go and start orbiting another body. Okay. This was just it had only an orbiter, and its goal was to do chemical, mineralogical and photogeologic mapping of the moon. It carried 11 instruments, and some of these instruments were actually from laboratories in other countries, okay, USA, Sweden and so on. After in addition to this orbiting spacecraft, one part of the mission, which was towards the end of the mission period, was to actually drop a payload onto the surface of moon, which was called the impactor. And while this instrument was dropped on the moon, it would do some observations and study some aspects of the moon's surface as it approached the moon. Okay. Now, this was a very successful mission, and as the things that I told you about the Mangalyaan were true also in this case, namely that this was our first mission to the moon, and in the very first attempt we got it right. We were able to perform a very accurate, a very precise insertion of the spacecraft into the moon's orbit. Getting captured into the moon's orbit and staying in an orbit around the moon was something that happened in the first go. This is a testament to excellent navigation, excellent guidance. And when I say guidance, it really means autonomous guidance and proper planning and computations. One of the main achievements of this Chandrayaan mission was that two instruments on this spacecraft gave us unambiguous signals, unambiguous evidence for the presence of water on moon. Okay. So, a lot of data was received, analyzed over the years. Different, and this presence of water was tested by two different instruments, and the results of the two instruments matched, and that is how this confirmation of the presence of moon was put out. This was one of the major achievements of the Chandrayaan-1 program. With the success of the Chandrayaan-1 program, we had more ambitious programs to explore the moon, and in 2019 it was planned to send a mission to moon, which comprised of not just an orbiter but also a lander, which means a vehicle that would land on moon, and another vehicle, a third vehicle, which would reach the surface and move on the surface of moon. Okay. But unfortunately, this mission, although the launch was very good, the spacecraft also reached the moon in the correct orbit, performed the orbital maneuvers and stayed in the orbit correctly. The lander part, which means the part that actually landed on the moon for exploring the surface in situ, it could not land on the moon correctly, so it failed to soft land on the moon. So, only part of the mission objective was met. But undeterred by this failure, the ISRO team put together the next Chandrayaan. Chandrayaan-3 was launched in July 2023. It too had a configuration consisting of an orbiter, a lander and a rover, and it successfully soft landed on 23rd August of last year. That is why this day today is being celebrated as India's Space Day. It is a commemoration of a very successful soft landing of the rover and lander on the surface of moon. The objectives of this mission were also of a purely scientific nature, and it landed near the southern polar region, and the observations that were done in situ, observations of the lunar soil and so on, has provided us evidence for certain theories about how the lunar surface has come into being. It has also detected the abundance of different elements in on the moon's surface or the moon's soil, and these data or these observations are useful for us to figure out how the moon, for example, came into being, and whether further exploration of the moon is meaningful or whether it is going to be advantageous, and so on. Now, with these three Chandrayaan missions, I think ISRO has come of age. It has been successful earlier in launching all kinds of communication satellites and other application related satellites, but now it is also gradually getting into the space exploration arena, and it has shown that we could do some good science using these satellites or these spacecraft. More recently, about 2 months after the success of Chandrayaan-3, another ambitious mission was started, and I have been fortunate to be part of this mission, which is Aditya L1. Aditya L1 is a spacecraft that has travelled already towards the sun and is now parked in a satellite in an orbit, which is an imaginary orbit around the Earth Sun axis, and it is meant to make constant continuous observations of the sun of different particles, light, etc., that is coming from the sun. Now, this is the first mission of its kind to what is called the first Lagrange point of the Earth Sun system, and this satellite has been launched. It is now stably parked in the orbit. It has completed one halo orbit as intended, and the instruments on this satellite are now functional. They are sending out data. With this satellite, with this spacecraft, we are hoping to understand the processes that go on the surface of the sun. How does sun, for example, emit the kind of amount of energy and the manner in which this energy is put out. It will help us understand various disturbances that happen due to the sun because of the charged particles coming out of the sun, because of the light coming out of the sun, and so on. This is a long-term mission. It will continue to send us data perhaps for the next 5-6 years, and it will enrich our understanding of the sun by giving us multi-particle, multi-parameter data in a very this is a satellite which is a very ambitious multi-instrument spacecraft and capable of giving very large quantities of very nuanced, very well defined observations. All of these satellites or spacecraft that have been launched with scientific objectives have given India's space program a completely different dimension, and this is in some sense the icing on the cake. The earlier satellites, which were primarily devoted to communication, mapping, remote sensing, and so on, were all satellites revolving around the Earth with a very clear application-based, application-driven objective. But here now we are looking at a new phase where we are exploring space, where we are looking at or observing different heavenly bodies, different sun, Mars, moon, and so on, with a very strong scientific objective, and that really sets these spacecraft apart from the spacecraft of the past. So, I would say that in the future we can hope not only to continue with our communication and remote sensing satellites as per our need, but there are also other things planned. So, for example, very recently a Chandrayaan-4 mission was announced, and this is going to be a sample return mission, which means that we should be able to bring back samples of the lunar surface. Then there is another program called the Gaganyaan, which is a human space flight program, and its crew re-entry module has been recently tested. So, the Gaganyaan program is also progressing, and there is another Mars mission in the pipeline, and so on. So, the future also looks bright. We have many things to look forward to, and we will continue, I think, to have a combination of application driven satellites and satellites for scientific research. So, what the space missions of our country have provided us are can be there are many aspects to it. So, first of all, they are very fascinating endeavors. So, they motivate people, they trigger your curiosity, and by and large they are capable of fascinating a large number of even lay people. There are huge technological challenges and there are remarkable technological feats, all of which gradually trickle down and become useful not just for space exploration, but for many other things that would be related to our daily lives. These space missions have provided us with useful data and services in the field of remote sensing, disaster management, weather and so on. And of course, for communication, all kinds of communication, whether it is satellite TV, whether it is internet, telephony, whatever. Then the other part, which are these explorations of other bodies, they permit us astronomical observations that would not have been possible from the Earth, and also help us understand the nature of heavenly bodies around us. This is something that I think humans have always yearned, mastered it to some extent. To explore these by either observing it from a more vantage point, or actually reaching that surface and collecting samples, or observing things in situ. Now, all of this has a very deep science connect. So, the entire technology that goes into science missions, if you trace its history, then you will find that what you learn in school books, school textbooks, can be related to what happens in a space mission. A deep understanding of science is necessary for the development of technology, any technology, and certainly for space technology. Okay. So, you could go right far back as something like Newton's laws, the third law of motion, which is actually the second law of motion, or by and large laws of motion, which are actually the principle behind the launch of a rocket or the functioning of a rocket. Or you could trace another thread, which is the atomic structure of matter, the ability to think of matter in terms of building blocks called the atoms and molecules, whose understanding leads us to better materials, different kinds of materials, all the way from the fuel that is needed for powering these satellites or rockets, to the materials that are needed to construct them, or the semiconductors that are needed for communication. Much of this development has happened with fairly abstract ideas in science, which once you understand the method of science, you build upon it, build upon the theory, put it into practice, do a lot of experimentation, and gradually come up to applications in the field of materials, in the field of communication, and a whole lot of areas which have touched our lives. So, to end, I would say that science and technology go hand in hand, and both are vital for progress, and not just progress in the domain of space exploration, but in practically any domain of life. With this, I will end. Hope you enjoyed the talk, and hope you continue to be fascinated by the space exploration that our country is pursuing and will continue to pursue in the years to come. Thank you.